or afternoon. Good morning or afternoon, depending on where you are joining us from. My name is Sarah Behdad. I am an associate professor in environmental engineering sciences at University of Florida, and I am so delighted to welcome you to the 11th thematic session of the Journal of Mechanical Design webinar series. This is a special webinar because this is a joint webinar between JMD and Journal of Manufacturing Science and Engineering. Today, we get together to learn more about the topic of advances in design and manufacturing for sustainability, which is an important topic for our own community and also for the broader audience worldwide due to the importance of the sustainable development field. This webinar actually is based on a joint special issue which was released last year in February 2023, and the main objective of that special issue was to combine the collective expertise of ASME Manufacturing Engineering Division and ASME Design Engineering Division together and learn about what is the latest research that is going on related to sustainability in our own field. And most importantly, to encourage collaboration or identify collaborative opportunities for the communities, MED and DED community. The call for paper covers different types of topics ranging from circular economy to sustainability analytics to human-centric design, remanufacturing, system efficiency, and decarbonization. A team of 9 associate editors was formed, and the team actually covers expertise from both JMD side and JMSE side. We would like to acknowledge the work of all the associate editor, Dr. Banu from University of Michigan, Dr. Daniel Cooper from Michigan, Dr. Carl Hoppola from Oregon State University, Dr. Chow Hu from University of Connecticut, Dr. Harrison Kim from University of Illinois at Urbana-Champaign, Dr. Astrid Layton from Texas A&M University, Dr. Barbara Linke from UC Davis, and Dr. Ji Zhang from UT Dallas. A special thanks go to all of these individuals since they devoted a significant amount of time to make sure about the quality and relevance of the submission for a special issue. Also, our gratitude will go to Editor-in-Chief of Journal of Mechanical Design, Dr. Caroline Sipperstad, and also Editor-in-Chief of Journal of Manufacturing Science and Engineering, Dr. Albert Shi, for their visionary leadership and a strong support of this webinar and also a special issue. Also, we would like to thank Amy Suski and also Emily Bosco for the significant amount of time that they devoted to this special issue, such that we basically can finish things on time and publish the special issue. Finally, the special issue was published in February 2024 this year. And we received submission from different range of topics. The encouragement and scholarly contribution of the community was very significant. The chosen submission can be categorized in 6 main categories: design for manufacturing, advancement in sustainability assessment, design intervention for user sustainable behavior, advancing disassembly practices, techno-economic analysis of energy system, and innovative tools for teaching sustainability. We would like to encourage all of you to take a look at this special issue and learn more about what is the latest research that is going on in our community. And we would like specifically to thank those who contributed to this special issue, and their encouragement and also a scholarly contribution is appreciated a lot. So this is the agenda for today's webinar. After introduction, I will invite Dr. Caroline Sipperstad, Editor-in-Chief of Journal of Mechanical Design, to give a few words about the journal. Then we will hand it over to Dr. Harrison Kim from University of Illinois to introduce our first 2 speakers, a feature talk from JMD side, and then Dr. Barbara Linke will introduce our speakers for JMSE feature talks. And after that, we will have a Q&A and panel session And my understanding is that the Q&A session is not recorded. Therefore, you could either put your question in the chat option of Zoom, such that we can collect and answer those during panel session, or alternatively, you may unmute yourself and ask question during panel discussion session as well. And finally, we have a gather town for a networking event at the end of the panel session. Again, we would like to encourage all of you to stay for the networking event, because the main purpose of this special issue and also this webinar, again, is to establish further collaboration within our community. With that, I will basically hand this over to Dr. Sipersat to give us a few words about JMD.
Okay, well, thank you, Sarah, and thank you for such a wonderful introduction to this webinar. There's not a lot left for me to say because you covered everything so well, but I just wanted to welcome the community to the webinar and thank Albert Shi, my partner over at JMSE, because it's been awesome to work with him on this joint special issue and joint webinar. So many of these webinars do, in fact, stem from special issues that we publish in JMD. And so I just encourage the community and all those who are listening out there, if you have an idea for a special issue that you think could be timely and impactful, contact us. Let us know what you'd like to do. And similarly, if you have an idea for a webinar, we typically carry out these webinars 3 to 4 times a year. So this is the 11th webinar that we've conducted, affiliated with JMD. They were started in 2021 by my predecessor, Wei Chen, who did an amazing job as editor-in-chief of the journal prior to me. So anyway, welcome to the webinar. Thank you to Sarah and everyone for organizing it. And also thanks to Fayez Ahmed, who's our special, who always offers special expertise in webinars for these. And we really appreciate all of his efforts behind the scenes. So I'll turn it back over to you, Sarah.
Thank you so much. Yes, now let's go back to the second item in the agenda, featured talk from JMD side. I would like to invite Dr. Harrison Kim to introduce our first speaker.
Thank you, Sarah. Thank you, Caroline. It's been a great work experience for serving as associate editor with the excellent group of colleagues representing design and manufacturing for this special topic. More than anything else, we're very, very pleased to see these excellent publications published for the special issue. So I'd like to thank everyone for their contribution. My role today is to just represent JMD's side to introduce 2 excellent speakers back to back. First speaker is from University of Toronto team, Alexa Rea. She obtained the graduate degree in mechanical and industrial engineering at the University of Toronto. Her research is focused on encouraging pro-environmental behavior through the product design. She specifically examines how to motivate energy-efficient temperature adjustment or control during user thermostat interaction by applying psychology-informed engineering design principles. So very much looking forward to this presentation. Alexa, please go ahead and share your screen, and the floor is yours.
Sure, thank you. All right, hi everyone. My name is Alexa Rea with the Department of Mechanical and Industrial Engineering at the University of Toronto. And today I'm going to present myself, Drs. Corbett and Shu's work, examining whether fan feel and visibility during thermostat interaction affects temperature selection, specifically more energy efficient temperature selection in warm ambient conditions. One of the United Nations Sustainable Development Goals is to address climate change and its effects. Specifically, air conditioning use consumes significant energy while contributing to greenhouse gas emissions due to widely used refrigerants. In a vicious cycle, higher global temperatures lead to an increase in AC use, which in turn heats the outdoors, further necessitating AC use. Therefore, the growing environmental harms associated with increased AC use motivated us to explore how to decrease its use. Next, I'll give a background on the range of behavior change interventions. At one end of the range, user in control, we have information and feedback-based interventions. And the goal of these types of interventions is to provide information and feedback to motivate a desired behavior. And an example of this type of intervention would be a thermostat with the message displaying, you would use less energy if you set a higher thermostat temperature in warm weather. However, one of the limitations of these types of interventions is that it requires a high level of user motivation and assumes that humans are rational agents who are capable of changing their beliefs and behavior in lieu of new information and feedback. At the other end of the range, we have product in control, so forcing and automation-based interventions. And the goal of these types of interventions is to make it impossible to avoid the desired behavior. So an example of these types of interventions would be setting a hard limit on the lowest possible thermostat temperature. And one of the limitations of these types of interventions is that it overrides user control. So it's making a decision on behalf of the user, and the user is not actually engaging in any meaningful behavior change. In the middle of the range, we have enabling, encouraging, guiding, and steering interventions. And the goal of these types of interventions is to alter external factors such as the physical environment or product characteristics to motivate a desired behavior. And it was the goal of the current work to examine the effect of these types of interventions on users' thermostat temperature selections. Next, I'll give an overview of the study. Energy inefficient behavior can be driven by sensory stimuli. So for example, a user who feels hot entering a warm thermal environment may set an energy inefficient temperature adjustment. So we wanted to explore whether product features could create sensory stimuli that would then affect the temperature adjustment behaviors. Specifically, we wanted to examine how the addition of mechanical fans, which of course use less energy than AC, could increase eco behaviors. And it's important to note that the features should consume less energy than the energy the intervention intends to conserve. So we hypothesized that by alleviating thermal discomfort through the addition of mechanical fans, that we could prompt more energy efficient temperature adjustments during user thermostat interaction. So our study combined two effects. The first was fan feel, so whether participants could feel the fan or not, and fan visibility, high versus low. And we had 4 combinations of these effects. So the first was feel fan high visibility. So here in this first condition, the fans were on and were in front of a clear cover. Next, don't feel fan high visibility. Here the fans were on, but were behind or encased within the clear cover. Third, feel fan low visibility. Here the fans were on, but were behind a ventilation grill. And finally, don't feel fan low visibility. Here the fans were off and were behind a ventilation grill. Next, I'll go through the experimental procedure. So first, participants entered a thermally warm space, and this fluctuated between 24 and 27 degrees Celsius or 75 to 80 degrees Fahrenheit. They then completed their thermal comfort assessment, and this was based on the ASHRAE 7-point scale of thermal sensation. They then set their baseline temperature. So we asked participants to think about what a comfortable temperature would be and to set the thermostat to that temperature. They then made that temperature adjustment on an actual thermostat. After that, they completed their baseline impressions, followed by a syllable counting filler task to reduce carryover effects between conditions. They then interacted with all 4 intervention interfaces. Since this was a within subjects design, participants interacted with all 4 interfaces. They then completed their interface impressions and finally a syllable counting filler task. Finally, participants answered post-interaction questions such as environment and thermal comfort assessment, manipulation checks, effect perception, and general, as well as more specific study feedback. And finally, value orientations, as well as energy myths to gauge participants' conceptual model of heat delivery. Getting into the intervention, interface, interaction details. So this is what it looked like in our laboratory setting. And we had participants complete 5 tasks. So task 1, we asked them to take 30 seconds to think about their thermal comfort in this moment and to write down how they were thermally feeling as they stood in the rectangle. And this task was devised to just collect more qualitative information about how participants were feeling as they were face-to-face with the interface. Task 2, we asked them to think about what a comfortable temperature would be and to set the thermostat to that temperature. A research assistant then collected that temperature. And tasks 3 to 5 were more exploratory, and these questions were completed on Qualtrics. So task 3, we asked what features stood out the most about the thermostat and if that affected how they used it. Task 4, we asked them what factors led them to select that temperature. And finally, task 5, we asked them why did they set the thermostat to the setting that they did. Next, to give an overview of our participant characteristics. So our sample consisted of 23 university student participants. And to break that down further, 20 were from a first-year psychology class and 3 were from the general university population. For gender, it was evenly split between male and female students, and 1 student identified as genderqueer. Age, we had 21 of 23 participants within the 18 to 24 years of age range, and 2 of 23 within the 25 to 34 years of age range. So first, examining our first result, we see that fan feel has the stronger effect. And first, examining temperature shift, which we used as a meaningful measure of behavioral change. And we define this as the difference in temperatures set by participants in their baseline condition as compared to the temperature set in each condition. And since temperature preference is so subjective and variable between people, we thought that it was important to essentially use participants as their own comparison point. First, looking at the effect of fan feel. So we see a significant effect based on fan feel. Specifically, participants set higher temperatures when they could feel the fan than when they could not feel the fan as compared to baseline. Next, looking at fan visibility, here we do not see any significant effect. So whether fan visibility was high versus low did not affect participants' temperature adjustment behaviors. And finally, looking at the interaction, we do not see any significant relationship. Next, examining raw temperatures. So this is just examining the mean raw temperature set by participants. So first, looking at fan feel, we see a significant effect based on fan feel. Specifically, participants are setting higher temperatures when they could feel the fan versus when they could not. For fan visibility, here we do see a surprisingly marginally significant relationship. So specifically, when fan visibility was high, participants are setting marginally higher temperatures than when fan visibility was low. And finally, looking at the combined interaction, we do not see any significant relationship. Next, we see that significantly different temperatures were set between interfaces. Specifically, higher or more energy efficient thermostat adjustments were made by participants in the feel fan high visibility condition as compared to baseline and the 3 other intervention interfaces. So by setting higher temperatures, this leads to an increase in energy conservation. So how do we interpret our results? So first, we see that fan feel effectively nudges energy efficient temperature adjustments. Specifically, higher temperatures were set when the fan was felt than when the fan was not felt. And when examining open-ended responses, we see that 20 of 46 responses indicated some type of improved thermal comfort. And this is illustrated by this one participant who noted that they were not as concerned about warm ambient temperatures as before when not interacting with the feel fan interface. Next, we see that fan visibility alone may not be sufficient, and that temperature adjustments were only marginally affected by fan visibility in the raw temperature analysis. A theme that emerged in the open-ended responses was this notion of visibility-induced frustration. So for a minority of participants, they reported that being able to see the fan but not feel its effects led to some frustration, which in turn affected their behavior. And this is illustrated by this one participant who noted that the promise of a breeze locked behind the glass frustrated them, prompting them to select a lower temperature. Finally, we wanted to discuss some implementation possibilities for the current intervention. So as covered, the study examined the effect of fan feel and visibility on participants' temperature selection. However, as just noted, fan visibility may not be necessary in order to cue more energy efficient thermostat adjustments. And since fan feel was shown to be the stronger effect, other configurations where participants can feel the fan may also be effective. And since we did want to ensure that fan feel and visibility were salient to participants, other fan locations and sizes are also possible. So for example, embedded within the thermostat would also be a possibility. And finally, we just wanted to note that person sensing technologies such as motion sensors or weight detection can save additional energy to ensure that the fans only remain on during user thermostat interaction. Finally, discussing implications and future work. So first, we see that fan feel increased energy efficient behavior without modifying beliefs. We also see that fan feel is confirmed as an effective, enabling, encouraging, guiding, steering intervention to reduce energy consumption. And finally, we see that fan feel consumes less energy than intended energy conservation. And finally, future work should address differences in fan speed. So for example, in the feel fan high visibility and the feel fan low visibility condition, we had the fans set to the exact same setting. However, since the feel fan low visibility condition had the ventilation grill cover, it did obstruct some of the felt airspeed, which did lead to some differences. So future work should ensure that there's as little difference as possible in felt airspeed for these two conditions. Next, temperature fluctuation. So as noted, the laboratory temperature fluctuated between 24 and 27 degrees Celsius or 75 to 80 degrees Fahrenheit. And while it could be argued that this simulates more naturalistic conditions, we should ensure that this factor is better controlled for in order to remove this as a potential effect. Next, diverse participants. Since we did use a student sample, future iterations should recruit a more age-diverse sample in order to determine the generalizability of these findings. And finally, since the user thermostat interaction took place over the course of minutes, future work should try and do this across longer time scales. So for example, across the day, weeks, or months to determine the efficacy of this intervention across these longer time scales. And the final key takeaway from our work is that external factors such as mechanical fans can be used to increase pro-environmental behavior during user thermostat interaction. So we wanted to take the time to acknowledge the University of Toronto Collaborative Specialization in Psychology, Psychiatry, and Engineering, also known as the PsychEng program, as well as exceed funding to support cross-disciplinary research. And finally, the Social Sciences and Humanities Research Council of Canada, who also funded this work. Thank you.
Great. Thank you very much, Alexa. Perfect. It's just 15-minute mark. So I see some of the activities in the Q&A session chatting window. Please pose your question, and we're monitoring those questions so that we can have discussion time at the end of the overall 4 presentations. Thank you. The next speaker is from Europe, representing Italy and the Belgium team. So I'd like to introduce Dr. Núria Rodríguez, who is currently working as a postdoctoral research fellow at KU Leuven. She is originally from Spain, and she majored in industrial engineering as well as life cycle engineering and eco-design. Her primary focus is on making products more eco-friendly and longer lasting by use of LCA, eco-design principles, and so forth. Her goal is to help create a greener future by improving how things are made and used. So as you can see, the lineup of speakers, this is a wonderful example of a diverse international community for which our two journals represent. So with that, Núria, could you share your screen?
Sure.
And the floor is yours.
Thank you. Okay. Can you see the presentation, right? Okay, so thank you for the presentation. I'm Núria Rodríguez, and as Harrison said, I'm a postdoc researcher here at KU Leuven in Belgium, and I will present the paper entitled Disassembly and Repairability of Mechatronic Products, Insights for Engineering Design, that was done in collaboration with Claudia Favi from Parma University in Italy. Okay, in particular, today we will see a brief introduction where I will explain the motivation behind this project, followed by the description of the method proposed, and then we will see the results and discussion through a case study. Finally, we will explore the conclusions and future works. The awareness of environmental and social responsibility, as well as the demand for sustainable products, has increased in recent years. The younger generations are the most dedicated to ecology and the environment, with 61% of millennials willing to pay more for sustainable and eco-friendly products. Social movements advocating for circular economies, such as Zero Waste Europe or Right to Repair, have empowered consumers. This growing demand for sustainable products from consumers, but also from the European political community, has driven the need to address sustainability and circularity in the design of mechatronic products. Europe wants to achieve circular economy by 2050, being product waste one of the main issues that industries are called to seek for sustainable use of natural resources. To face this concern, manufacturers and designers are encouraged to increase the lifespan of their products, adopting specific target design methodologies, such as design for durability, repairability, or upgradability. During past years, numerous tools and new standards have been developed to assess the product's ability to be repaired, such as, for example, the French Repairability Index, which is already in use for 10 product categories, the Matrix for Ease of Repair, the EDIM, or the scoring system for the repair and upgrade of products, which was used as reference in the development of the EN 455054 standard. Okay, the goal of this research was to define a design methodology and associated decision-making tool to derive and implement eco-design rules focused on disassembly and repair in the design of mechatronic products. Now we will focus on the method that we proposed, which aims to include the repairability indicators during the design phases for this kind of products. It is a systematic approach that can be performed iteratively to optimize the sustainability score of the analyzed product. It entails 4 main phases. The first one is the identification of target components, followed by the experimental disassembly analysis. Then the third phase is the disassemblability index assessment, and the last one is the eco-design methodology implementation. So for the first phase, what we need to do is to define which parts or components of the product will be studied. These target components are those with higher failure rate or that are critical for the proper functionality of the product. Then for the second phase, that's a key step for the repairability assessment. And here we will need to disassemble the product manually or virtually in order to collect all the data to calculate the disassemblability index. This research is based on the horizontal standard, so the information that we require includes the number of steps needed to remove the components, the type of fasteners that are present in the product, the type of tools, and the disassembly time. For the third phase, the assessment of reparability, there are several scoring systems, as I already explained, and most of them always identify the same disassembly criteria. For this research, we have focused the analysis on the disassemblability index, which is described in the JRC report and the Sensenelec standard. So as shown in the table, the disassemblability index is a component of the repair scoring system. And we have these 4 parameters, the disassembly depth, fasteners, tools, and disassembly time. And the decision of address just the disassemblability index rather than the overall RSS tool was motivated by our aim to address engineering eco-design solutions aimed at improving reparability from the designer's perspective. That is why we excluded parameters that were not strictly related to engineering design. Here in this slide, we can see the equations or tables that we use to calculate the different scores for each parameter. So for example, for the disassembly depth, what we do is to compare the number of steps to remove the selected priority part with a reference value. This reference value represents the reference number of steps for the removal of that target component given a specific product family. As we can see, if the disassembly depth for our priority part is equal or greater than the reference number, the score is 0. The scores ranges from 0 to 1, being 1 the best scenario possible. The most common approach to establish this reference value is to perform a benchmark analysis and retrieve this value as the maximum that we can find in this analysis. Another approach can consist of performing a techno-economic analysis of the product and assigning a target value that makes the repair operations economically feasible. Then for the fasteners, we analyze the type of connectors that we are using, categorizing them based on their reusability, whether they are reusable, removable but not reusable, or not removable. The same strategy is applied to determine the types of tools needed, depending on the category, if it's a common tool, a group-specific tool, etc. And finally, for the disassembly time, we follow the same approach as the one used for the disassembly depth. So we compare the time that we need to remove the target component with the reference value. This disassembly time is calculated using the ease of disassembly metric, which is based on the MOST technique. Shown in the flowchart here in the slide, to determine if the current design meets the required standards, we compare the scores with a predefined threshold. The definition of this threshold depends on different factors, such as the characteristics of the product that we are analyzing, for example, the value of that component, or the company's know-how, understanding the failure rate for that specific part. Also, we can use the cost-benefit analysis of the reparability scenario. To streamline the redesign process, we establish individual thresholds for each disassembly parameter that enables to identify the main cause of criticality more effectively. Finally, the last phase is the eco-design methodology, and it involves implementing eco-design actions. And for this phase, we compare the results obtained with the thresholds that we already established. So these reference values were validated through a cost-benefit analysis and the ROC curve method. As shown in this table, we have assigned a mathematical rule to each parameter, indicating the action needed to address that particular problem. Now we will see briefly the case study, which was a combi steam electric oven. It's a part of the household appliances sector. So for this product, the target components that we defined are the user interface, the hot air motor, temperature sensor, lamp, cooling motor and fan, etc. Once we have the list of target components, what we need to do is the disassembly. We perform a manual disassembly test at the university facilities in Italy. And in this table, we can find a summary of all the data that we collected, including the number of steps, the tool that we use, the fasteners encountered, etc. Okay, once we have the data, we need to assign different weights in order to set the priority of the different target components. In order to do that, we use this matrix, which is the failure rate, failure impact matrix. And once we establish the weights, we can calculate the disassemblability index results. And as we can see, all the scores, most of them are lower than 0.5. So they are considered high critical components right now. Okay, after the evaluation of the disassemblability index and the identification of best and worst practices through different meetings with engineers and also design experts, what we did was to establish some eco-design guidelines. Those guidelines are shown, are used, for example, in this slide. So we can see for the target components, top heating element, user interface, and door glasses, the mathematical rules and the eco-design action that we will use in order to address the criticality. For example, for the user interface, the main criticality is the fact that the number of steps that we need to remove it is the highest one in the market analysis. This is due to the vertical design that this component presents. And what we suggest is to suggest to the designers to allow the removal of the front panel where the user interface is placed without the need to disassemble additional components. For example, right now we need also to disassemble the back panel and the top panel. So we want to create a more horizontal design for this part. Here, we will see more in detail some eco-design actions that we propose. For example, for the top heating element, one of the main criticalities was the tool needed to remove. This clamp was considered dedicated or specific tool. So the score was 0.75 out of 1. So we suggest to change this kind of clamp that can be removed using just a flat screwdriver, and the score goes to 1. Another example is the case of the door glasses. Here, the problem was the use of adhesive, and the proposed solution also involved the selection of reversible fasteners. Again, we are using screws. So once again, we can achieve the maximum score possible just changing this joining method. Okay, after applying the proposed actions, we can confirm that the disassemblability score is no longer high critical for those priority parts that we address, but these actions that we are proposing not only affected the disassembly, the reparability score, but also other design for X parameters. In this table, we can see a qualitative score to assess whether the action has positive or negative impact on design for assembly, manufacturing, cost, and reliability. For example, we can see how changing the clamp for the top heating, as we suggested before, has a negative impact during the assembly, since the original clamp was used to facilitate this aspect. But we can also see how the general impact for this action is positive, since thanks to that change, we improve also not just the disassembly, but also the reliability by facilitating maintenance or repair. So as explained before, there are different approaches to define weights for parameters or weights for target components. So initially, we assigned higher weights for disassembly depth, fasteners, and disassembly time, while for the tools, the weight was lower. The reason behind this is it was based on literature analysis for this product category. But then we perform a sensitivity analysis to observe the impacts of these changes on the outcomes. So we can see that reducing the weight of the disassembly depth increases the results by an average of 12%. While for the door glasses, it is just 1%, since here the main criticality was the connector, the adhesive, not the disassembly depth. On the other hand, when the weight of the fasteners is reduced to 1, a general decrease in the index is observed, and this parameter was not critical for most components. However, as I said, for the door glasses, It is the only priority part that increases the index result by approximately 14%. Similar results to the ones from scenario 1 are observed when modifying the weights for tools or time parameters. So in conclusion, I would like to just remind that repairing plays a key part in achieving circular economy. This research introduces a methodology based on the disassemblability index that aims to improve repairability on mechatronic products. We tested the method with a case study in the field of household appliances, demonstrating that this framework is valuable for engineers, but also for designers. Using a virtual prototype, we were able to implement several eco-design actions and reassess the new disassemblability index, observing an average improvement of 31% after the implementation of all the actions proposed. As future works, there should be a focus on incorporating additional parameters to conduct a more comprehensive assessment. Additionally, testing the method across other product categories would be also beneficial. And finally, conducting a more in-depth sensitivity analysis to assess the robustness of the index is necessary. And not to forget to facilitate the adoption. At the end, what we will need is to put efforts trying to integrate this method into software programs to really help designers. So thank you very much for your attention.
Thank you, Núria. Just exactly 15 minutes on time. Excellent presentation. Once again, I'd like to invite the audience to write your questions. We're monitoring, and then we're going to share those during the Q&A time. I'm going to now hand over my microphone to Professor Barbara Linke.
Yes, thanks. So yeah, it's my pleasure to now introduce the two talks that were hosted from JMSE, from the manufacturing science and engineering side. So the first talk is by Abigail Clarke-Sather from the University of Minnesota, Duluth. She's an associate professor there in the Mechanical and Industrial Engineering department. She holds a BA in physics from Earlham College and a graduate sustainability certificate, MS and PhD degrees in mechanical engineering from Michigan Technological University. Previously, she worked at the University of Delaware in the civil and environmental engineering and fashion and apparel studies departments. Dr. Clarke-Sather welcomes collaborations on real-world applications on sustainability, engineering for global development, life cycle assessment, and textile recycling through her research lab, the Applied Sustainable Product Innovation and Resilient Engineering Lab, abbreviated ASPIRE. So we'll welcome your talk and stop the screen sharing so you can go ahead and please get started.
Thank you so much for the introduction. I'm here to talk about some of my recent master's student, Paulo Alva's work that we worked on textile recycling, and that was combining flexible and sustainable design principles to evaluate designs, particularly for a mechanical textile recycling system. As you may be aware of, textile waste is a huge problem, both global and within the US. And globally, that means that there are millions of tons of fibers that are produced per year, and that the apparel and fiber and textile industries are responsible for 10% of greenhouse gas emissions worldwide, as well as a large percentage of global clean water pollution and primary microplastics release. In the US in particular, in terms of what happens to textiles once they're unwanted, of the 15.6 million tons annually of textile waste that are created, less than 15% are recycled. And so this is a big problem. There's a lot of opportunity to handle this. What happens currently for these textiles here we have a great system view of kind of what's going on at the end of life of textiles. So we can have reuse that happens. We can have open loop recycling back into new products from discarded apparel. There can be kind of service economies in terms of renting, and then also fabric or fiber recycling that happens within the original manufacturing process. The focus that we're looking at here is really fiber recycling and looking at how mechanical textile recycling can be a part of that and what effect that has on design. So one of the things I know all of you have probably heard of the 12 principles of green engineering, and these principles have been around for a while. They came from the 12 principles of green chemistry, and there really was time to start thinking about what might be missing from these principles. And one of the things that seems to be missing on some level is flexible design. And so here is a review of 3 different papers that looked at flexible design for vastly different systems. So the Andro-Daughter et al. Looked at computer servers and networks. Su and Wang looked at outdoor furniture, including things for bike racks that are used in urban environments, and Spiller et al. Considered wastewater treatment systems. And so looking at these vast range of principles around flexible design, they were able to start to see some connections for where flexibility, what these flexible design principles already connected. So if you look at this idea of being robust or responsive to changing circumstances or adaptability to change, that fits really well with kind of some of the ideas in principles of green engineering in terms of meeting the need as it exists instead of having excess capacity. This fits with this idea of robustness already. It's not the same, but it's similar in response. So we kind of identified flexible design principles that really only existed in these different concepts and ideas with italics, and then the principles of sustainability that didn't necessarily exist in these flexible design ideas. So really we're trying to come together by bringing these ideas together to be able to adapt to our changing environment and changing situation brought upon by climate change and many other concerns by adding flexibility to sustainability when designing. From looking at these 2 different areas of design principles, we came up with our proposed principles designed for sustainability and flexibility, DFS Flex, and we actually chose to focus these principles along 3 different areas that seem to be present, both with flexible design and with the 12 principles of green engineering. You can see here that bold principles are representing things that came from those 12 principles of green engineering. Italicized principles are representing principles that came from flexible design, and when there's both, they were present from both. And splitting or organizing these principles into 3 areas kind of helps elucidate what those principles affect. And those 3 areas we considered were the design of the system, the material of the system or product, and then the process that the product did through function or the process that it was involved in producing. So these kind of 3, this new set, or I guess recombined set of principles, reorganized, is what we chose to take a look at mechanical textile recycling. So I wanted to talk a little bit more about what do we mean by mechanical textile recycling, and provide the expectations that we had for it. So what we're looking from mechanical textile recycling is really high quality fiber output. And that means that high enough quality that it could be reused in the original product that was made. So a lot of discarded textiles in the US are discarded apparel. And so it needs to have long enough fibers and quality fibers that could be used enough for apparel again. The other thing is really decreasing this process loss that happens. And that process loss is really just dust. And because the output that you get from mechanical recycling tends to be textile pieces, which would require more recycling or processing to be reused, yarns and fibers. Yarns and fibers have reuse applications, the textile pieces don't, as well as there will be dust, and so reducing the amount of waste through dust is desired. This is what that kind of looks like. Dust is really hard to see. Fibers are kind of fluffy and opened, and yarns still have some of that integrity that comes from seeing the fiber twisted together or plied together if there's multiple yarns. Textile pieces, this kind of top one very much looks like an existing textile. Some of these other pieces, you can see some of that interlace structure. This is from woven cotton denim. These are all woven cotton denim examples. And you can see some of that integrated structure that still exists where you can see the weave of the pieces. And so again, just this is what we expect to get, but we're trying to get to fibers and yarns, which can be respun into yarn again and potentially reused directly into new textile products. So how did we go about this? We designed a system that briefly involves carding wire, which is also called carding cloth, involves drums that are wrapped with that and feed a textile to that carded drum. This, of course, the first design did not result in exactly what we thought. So here we're looking at pretty much t-shirt material, 100% cotton knit, and some of the results. And here's my here's my graduate student, Paulo. And so we were able to shred it, but we had to refeed to actually get this down to fibers because you're seeing a lot of textile pieces, but not our desired output. That led to a variety of design changes, including changing the way that we connected the motors to the systems. And what happened is that we ended up getting clogging when we did the feeding process with our second design. We got clogging between the machines and the wall, and we created a barrier to keep the fibers circling between the drums, and the fiber would spill over them, and we didn't quite have enough torque to both control the feeding drums and then the shredding drums. That led us to our third design. We kind of extended a drum cover. We removed the feeding drums. We used the motors just to power the shredding drums, and then added air nozzles to funnel material that fell away from the shredding carding cloth surface. So this final design is what we ended up evaluating. And in order to evaluate it, we not only looked at the design principles, but we looked at how did it perform relative to our expected outputs. So this kind of shows visually our testing approach in that we started with fabric that was known. We cut samples to the same size, and then we put them in a relative humidity and temperature chamber so that they were conditioned all to the same temperature and humidity. From that, we fed those the same number of strips into the machine under different processing parameters, and then counted manually the output, weighing both the fabric samples after conditioning and directly before shredding, and then directly after output. So we varied several processing parameters, including different speeds. So this is representing speeds of the largest drum here in terms of RPMs, rotations per minute, and then different processing times. And again, so we have different processing times between 30 seconds and 90 seconds. And as you can see, and here we're looking again at outputs of textile pieces and then fibers and yarns together. So what you can see is that as we increased the speed of the drum, we noticed a slight increase in dust. That's kind of the dark band at the top, but a significant decrease in textile pieces. And we can see by comparing, here we've got statistical comparison of the percentage of dust, yarns and fibers and textile pieces across all the pairs, as well as using it was a non-parametric, so we're using the Kruskal-Wallis test and then Tukey-Kramer all pairs comparison post-hoc processing test. That's the circles that you're seeing here. So what we're seeing here is that at that E, so 90 seconds of processing has a significant different amount of dust as some of the very low speeds, but more importantly, that there is a very significant difference in how much yarns and fibers, the expected and desired output, are at E than the low speeds. And these also, you can see a very different amount of textile pieces at A, the lowest speed, versus the highest speeds. So thinking about the design of the fiber shredder and how it related to the DFS Flex principles, three researchers, including myself, who had intimate knowledge of how the fiber shredder worked and designed and had used it, evaluated separately for each DFS Flex principle. And we ended up evaluating both the design of the fiber shredder and then the process itself. So kind of the physical architecture, the components, and then as well as how the process was performing for the desired output. There also, we have kind of a description of how we rated these, both for design and then for process. In terms of the design of both the fiber shredder design itself and the process, there wasn't total agreement among all of us amongst many items. There were a couple of places where amongst the three raters, there was agreement about really meeting those principles. So in terms of material design for separation, in terms of the design was met and assumed to be met by all of us. There also was agreement on the negative side about in the process in terms, so the underlines show where we all agreed that material that could be hazardous might be created, especially if we're using in terms of microplastics for polymer-based materials. So that was a concern that was identified through this. And then in terms of the process, we all raters agreed that facilitating resource recovery was embodied by the process in terms of repurposing and recycling this product textiles successfully. Finally, we all agreed that in terms of the process, in terms of integrating material and energy flows, that it relies on non-renewable sources of energy. And that, again, is another place that we could look at the process in order to improve it. So this is kind of a shortened discussion of all of this, but in conclusion, we're still designing and still working on improving both the design and process. And this approach helped us think of ways to focus those efforts. And we'd just like to thank the National Science Foundation and Minnesota Sea Grant for funding this research.
Fantastic. Thank you so much. Yeah, there. I know we have a couple of good questions in the chat for later, but we'll move on to our fourth talk from Kamyar Raoufi from Oregon State University. To introduce Kamyar, I'd like to say a few words. He's a postdoctoral scholar in the School of Mechanical, Industrial, and Manufacturing Engineering department at Oregon State University and works with his co-author on this paper, Dr. Karl Hapler. He worked on research during his PhD career funded by the National Science Foundation and collaborated with students and researchers from many different universities, including Iowa State University, Pennsylvania State University, and Wayne State University. Kamyar also participated in an NSF supplement project at a consultancy company, Earthshift Global in Maine. He also led research under a seed grant from OSU HP to characterize the sustainability performance of competing conventional and additive processes, including a new HP 3D printing technology. Dr. Raoufi received the College of Engineering Outstanding Graduate Research Assistant Award at Oregon State University and completed the PhD in Industrial Engineering in 2020. So we're interested in this talk, and I'll stop sharing so you can go ahead, and the floor will be yours as well.
Perfect. Perfect. Thank you again, and sorry for the disconnection that happened. So today, actually, I'm going to talk about the manufacturing process and system sustainability analysis tool, which was developed in my PhD program, supervised by Dr. Karl Hapler at Oregon State University. So I'm going to start with a brief introduction and motivation of this research, followed by the research task that I did under this research, and then demonstration of the methodology and the framework that I developed, as well as the conclusion and the future work. So we know that the product design phase actually accounts for 5 to 7% of the total product cost, but about 70 to 80% of the product entire cost is going to be evaluated and estimated during this phase. This will be also the same for the environmental impacts. This actually shows the significant impact of design phase on the sustainability performance of the design. And actually the activities through supply chain logistics and manufacturing processes need to be investigated. And here in this research, actually I focused on the cradle to gate product lifecycle scope, which includes the raw material extraction, material processing, and manufacturing processes, as well as all the transportation activities to deliver the raw material from the suppliers to the selected manufacturers. However, this kind of assessment for non-experts who actually define under this research as in decision makers who do not possess a specialized knowledge in sustainability analysis of product designs and manufacturing processes is going to be challenging based on the multidisciplinary nature of sustainability and such assessment. So one enabler here to address this issue is the engineering education. And we know that like educators have developed several methodologies and actually have applied ad hoc approaches to conduct sustainability impact assessment. This research actually, and the objective of this research was to facilitate simultaneous analysis of sustainability performance impacts of different manufacturing processes and systems through unit manufacturing process modeling or UMP modeling within an easy-to-use, publicly available product design and manufacturing analysis tool. So the research tasks to achieve this objective was, first of all, identifying the relevant methods and software tools for analyzing product design, supply chain, and manufacturing process sustainability performance to identify what are the gaps and what are the advantages or somehow the drawbacks of each of these software tools or the methodologies and methods. Second, to establish a framework that integrates product design and supply chain information within a mechanistic UMP modeling approach for quantifying manufacturing sustainability performance. Third, to develop a publicly available product design and manufacturing analysis for non-experts that I defined earlier to conduct manufacturing process and system analysis under the lens of sustainability performance. And finally, to evaluate the operational performance of the product design and manufacturing analysis tool in terms of the ease of use and usefulness metrics. However, while this research actually contributes to the engineer education as well, but the main focus of this presentation and this paper was to focus on the technical aspects of this proof of concept tool, and this framework does. I'm not going to talk about the, task 4, which was focused on the operational performance of the manufacturing process and system sustainability analysis. And I'm going to be focused on these 3 main tasks for this presentation. So research task 1 was to focus on methods and software tools to identify the gaps that have been in the literature. So existing sustainability assessment software tools and methods have some limitations. First of all, we know that the eco-design software tools often require costly licensing and are not easy to access. This is one of the main challenges for non-expert decision makers to get access to these software tools for conducting sustainability assessment. Second, we need to have domain expertise to produce some meaningful results. By domain expertise, I mean the knowledge of eco-design issues and existing eco-design tools, and actually the concept of life cycle assessment, the life cycle inventory, how we need to capture the data, and all of those topics related to life cycle impact assessment. Third, LCA tools in perform manufacturing analysis rely on product mass. So that actually means if you have 2 different products with different features or different geometries, but if they have same mass, probably in terms of conducting the life cycle assessment, you need to, since they are mainly focused on the mass of the product, they will have some sort of same impact assessment. Also, methods and software tools capable of conducting quantitative sustainability assessment during the product design phase, which actually focus not only on only 1 or 2 aspects of sustainability and focusing on all the aspects, and also software tools that are needed, which are simple and user-friendly. In addition to having domain expertise, software tools themselves need to be simple and user-friendly. Thus, in research task 2, I focused on developing a framework for non-expert decision makers, and I'm actually by framework some sort of educational framework for these non-experts to be able to conduct sustainability impact assessment during the design phase. And here, the life cycle stage, as I described earlier, was focused on the cradle to gate life cycle scope, and the process characterization is based on UMP modeling, and all 3 aspects of sustainability are considered. So here is the framework that actually I developed. So first of all, in the first phase of this framework focuses on the product development, which includes 6 activities and 6 steps, which starts from defining the product idea up to generating the detailed design. The second phase is supply chain configuration, which starts from selecting the raw material suppliers, selecting from 2 locations, selecting transportation modes and routes, and developing the mathematical models for conducting the sustainability assessment for the supply chain activities and these logistics. The transportation and different upstream energy consumption and carbon footprints. The third phase is manufacturing process design, which starts with selecting the required unit manufacturing processes or UMPs for making the intended product, developing the mathematical models for each of those UMPs, and then defining the process parameter values for conducting the assessment itself. And finally, we have the MAPS sustainability analysis, and that MAPS word stands for manufacturing process and system. which is applying the models which have been developed in the previous phases. I mean, like the developing mathematical models for the supply chain configuration and manufacturing process design, conducting the sustainability assessment, and analyzing and comparing the results. So in task 3, which was developing a proof of concept, here is actually what I focused on. So in terms of the ease of use of the method, here, based on the accessibility of the tool, I focused on providing that publicly available and online. And also I developed a repository for that. So input of data information is based on the user entry of data. Manufacturing information is obtained by the UMP modelings, and the main objective of the analysis was on the evaluation, not on optimizing the product design. And here are the elements that are actually exist in the MAP sustainability analysis tool. So you can see that the design information based on the geometry or material, as well as the process steps and parameters, are captured to quantify the economic, environmental, and social impacts. For the economic aspect, I have 7 cost categories, which are tool, consumables, raw materials, facility, utilities, tool maintenance, and labor. For the environmental impact assessment, I focus on energy consumption and carbon footprint. And for the social impacts, I focus on number of injuries and illnesses and days away from work, which I developed 4 indicators and 4 metrics for quantifying the social aspect. And finally, we will have the economic, environmental, and social impact assessment. And here is like the mechanism of the proof of concept. So you can see that for each of the phases of the framework, the user can interact with the module specified in the proof of concept. And by providing the information by the user, the tool is going to do all of the math and calculations and all the, applying all of those models. Because in the framework, we had some activities and some steps in terms of developing some mathematical models. These are the sections that we are not expecting from the non-experts to conduct. This is actually the part that has been developed under this proof of concept for these non-experts to be able to conduct a sustainability assessment. Thus, they can easily select some numbers or values from the drop-down menus, for example, in each module, or provide some of the data and some parameters for the product design to be able to conduct a sustainability assessment for all the 3 phases of the framework. So here for phase 1, in terms of having a repository, here actually I focus on developing a repository for drones and multi-copters, which was done by some of our high school interns that participated in our research lab in summers of 2017, 16 and 15. So the main responsibility was actually playing with these drones to capture their lifting power while the batteries were fully charged, and then doing some disassembly, and then providing the CAD files of each of these components. And here is like a screenshot of the part specification module. You can see that we have some sort of drop-down menus here for each of the raw materials. Like if it's based on the plastic raw material, or if it is metal, then we can, non-experts can select what type of material they are using. For supply chain configuration, again, here we had developing the mathematical models. And this actually was, all the routes and distances were defined based on distance calculators, and average emission factors for various transportation modes were used here. And also for social impact assessment, as I explained, I developed 4 indicators. The first one was number of injuries and illnesses for transportation activities, and days away from work for transportation activities as well. And here is again the interface and kind of the screenshot of the supply chain configuration module, which has some from, to locations, the type of destination, if it's a connecting city or if the manufacturing city, and the type of the transportation mode. So then the average distances and the upstream carbon footprint will be calculated for the non-experts based on what they have selected in the previous steps. And developing the mathematical models for manufacturing processes. So here we actually start with the manufacturing process design approach, which captures the functional requirements, process requirements, manufacturing process flow, manufacturing process step analysis, and then the cost categories. For the environmental impact assessment, I use the process modeling, input-output modeling for capturing the environmental impact. And under this model, actually, for the plastic part production, in this proof of concept, I have the 4 UMPs for the plastic parts and 5 manufacturing processes for metal parts. And under this research, actually, I developed a mathematical modeling for metal injection molding manufacturing process, which was also included under this proof of concept. And similar to the transportation activities here, we have a number of injuries and illnesses and days away from work for the manufacturing processes as well. And here is like the manufacturing parameters that are required. If, for example, the user is going to select unit manufacturing process, for example, the plastic injection molding, then we only need 2 pieces of information from that user, like the machine clamping force and the number of cavities in the die. Based on these 2 inputs and based on these 2 process parameters, then the module is going to do all the math and calculations based on the product intended design for making the final product. And so here I have 2 representatives.
Sorry, Kamyar, 1 minute left.
Sure. And here is the representative supply chain configurations based on like the product designs that I have based on the number of propellers and blades and supply chains. And here are the the pie charts that the proof of concept actually provides for the user. Here we have the unit cost breakout by category for making the propellers based on different annual production volumes. Same thing for the shells. At 1,000 units per year compared to 100,000 units per year, you can see that what are the main drivers of the cost. The carbon footprint associated to the propellers and shells for both product designs, a number of injuries and illnesses, and days away from work for each of the manufacturing processes and supply chain configurations. And here, so the conclusions actually was the methods and tools to evaluate sustainability performance, as I actually explained. They have some limitations for enabling non-experts to conduct a sustainability impact assessment. So which were like the main expertise, having the kind of relating sustainability information to the product conceptual design is somehow challenging for non-expert, and actually the costly licensing. And also they rely mainly on the product mass and somehow focuses on 1 or like 2 aspects of sustainability impact assessment compared to having all the 3 aspects. That being said, I'm gonna thank National Science Foundation for financially supporting this research, and also the Research Seed Fund project supported by OSC and HP. And I will be happy to take questions if any. Thank you again for providing this opportunity to present my work here.
Fantastic. Thank you so much. Yeah, I think this closes out the recorded part of our webinar. Thanks again to all the speakers and very interesting talks. And we have a couple of questions we want to discuss before we go to the Gather Town. So
awesome. Yeah, and Chris,